Additional exercises of unit 12 nature of radiation and matter. Okay, question 20. Estimate the speed with which electrons emitted from the heated emitter of an evacuated tube. Potential difference is given 500 volts. Okay, then specific charge or charge to mass ratio E by M is given 1.76 into 10 power 11 coulomb per kilogram. Now, here you are asked to calculate and estimate the speed of electrons. So we have energy of the electron EV when it is accelerated by a potential. Its energy is EV or QV, etc. We say work done is equal to QV. You have studied in the second chapter. Is equal to half mv square. Half mv square. And from this we can have velocity v is equal to under root 2 ev by m. Substituting the values, you will get the speed of electrons. Here E by m is given, so directly you can substitute E by m there. Then part B, use the same formula to obtain the speed of electron when it is accelerated through a potential difference of 10 megavolt, 10 power 6, 10 into 10 power 6 volt. Okay, so here again you use the same formula. Okay, V is equal to under root 2 EV by M. Then we can see there you will get an answer. Okay, in this case you will get an answer in the order of 10 power 9 meter per second. You know, 10 power 9 meter per second means it is more than the speed of light, and according to our concepts, it's not possible. So where is the mistake then? So, you know, in such situations, when the electron is accelerated with such a high speed, then its mass is not a constant. Its mass changes according to the relativistic mass variation. M is equal to m naught, where m naught is the rest mass, 1 minus v square by c square. So if you want to get the correct answer here, in this case, I told you this answer is wrong. If you want to get the correct answer, in this formula, you have to substitute in the place of m, you have to substitute m naught divided by under root 1 minus v square by c square, then only you get the correct answer. When you substitute this formula, m is equal to m naught divided by under root 1 minus v square by c square, you will get an answer which is less than 10 power 8 meter per second. Now come to question 21. Mono energetic electron beam with electron speed, okay, 5.2 into 10 power 6 meter per second. Magnetic field is given. Specific charge E by M is also given. Okay, and you have to calculate what is the radius of the circle traced by the beam. You know, in magnetic field, a charge follows circular path with the radius of the path R is equal to mv by bq. Here instead of q you can take E. So it is electron. So that's equal to, again, E by M is given in the question, so you can rewrite this one as V divided by B into E by M. Now you can substitute the values there, then you can find the answer. Again, here part B, you can see there is a small change, that is the accelerating voltage. Instead of accelerating voltage, here energy is given. Energy is 20 MeV. Energy is. Now you have to calculate the same for 20 MeV energy. When you calculate the same for 20 MeV energy, So what do you have to do? Directly you can go for calculation. Okay, using the formula half mv square is equal to E into capital V. From there you can find the value of V. Okay, you will get V is equal to under root 2E capital V by M. So here also when you calculate, when the energy is that much high, when you calculate, you can see there the value will be more than the speed of light. Again, you can see in such a high energy, you need to consider again relativistic mass variation as we have seen in the previous problem. So here this mass m, you have to take as m naught divided by under root 1 minus v square by c square, then only you will get a correct answer. Okay. So relativistic mass variation must be used in this case also. And it's given that in both the questions 20 and 21, the part to be is beyond the scope of this book. So it's not very relevant for you. Then question 22, that potential difference is given around 100 volt, magnetic field is 2.83 into 10 power minus 4 Tesla. Radius of the circular path is 12 into 10 power minus 2 meter. These are the data given there. Okay, now determine E by M from the data. From the given data, E by M you have to calculate. So what can be done for that purpose? Again, you take half mv square is equal to EV. Now, from this equation, you find the value of v square. Just let it be v square only. V square is equal to 2 EV by M. 2 EV by M. Now, we know the force acting on the electron in a magnetic field. Okay, is F is equal to BQB, magnetic force. F is equal to BQB. So magnetic force is equal to BQV as it is electron. I will write BEV. Okay, because we have used E in the first question also. So BEV is equal to, as a particle moves along circular path, it will be centripetal force mv square by r. Centripetal force mv square by r. Now, from this equation, again, first you find the value of v from there. You will get a v is equal to EB r divided by m. Once you get the value of v, square the equation, find the value of v square. V square is equal to E square b square r square divided by m square. Now you have two equations for v square. These are the two equations. Equate them. After equating, you find the value of E by M. Equate, simplify, and find the value of E by M. You will get a final formula 2V divided by R square B square. Now you see the data given in the question. You can have a potential V, magnetic field B, and radius R. Substituting the values, you will get a E by M of the particle. Then question 23. X-ray tube. Wavelength is 0.45 angstrom. What is the maximum energy? So energy, we can use the formula E is equal to hc by lambda. We want to get it in electron volts, then you can divide it by E also. Substitute the values, you will get the answer. And part 2b, from your answer to A, guess what order of accelerating voltage for electrons is required in such a tube? Okay, so here you calculate the value in electron volt. Approximately your answer will be around 27.6 kilo electron volt will be the approximate answer here for energy. So what should be the accelerating voltage? If 27.6 kilo electron volt is the energy, then accelerating voltage will be 27.6 kilovolt will be the accelerating voltage. And you are asked what should be the order of the voltage. So you have to find out the next full digit only. So if we can go around 30 kilovolt. Okay, here it is 27.6 kilo electron volt is the energy. Corresponding voltage is 27.6 kilovolt. So when you round it, okay, so you will get around 30 kilovolt to be an approximate accelerating voltage. Come to question 24, an accelerator experiment. Experiment involving collisions. Okay, the total energy is 10.2 billion electron volt. Billion means 10 power 9. It is given here 10 power 9 electron volt, and it two gamma rays are formed. Okay, so an annihilation process, so that you can see an electron positron collision will give you two gamma rays. Okay, then what is the wavelength associated with each gamma ray? The wavelength associated with each gamma ray you have to calculate. So here energy is given. For the energy associated with each gamma ray is equal to, you will get 10.2 into 10 power 9 electron volt. So electron volt you have to convert into joule, or 0.6 into 10 power minus 90 divided by 2. What is the reason we need to take divide by 2? Because we have two gamma rays are there. The total energy is supposed to be distributed equally for both the gamma rays. So that is equal to hc by lambda. Now lambda you can calculate. Now next question 25. Okay, so it is about photon number again. Photon number. Part A. Number of photons emitted per second by a medium wave transmitter of 10 kilowatt power, emitting radio waves of wavelength 500 meter. Again, number of photons per second, N is equal to power divided by energy. Already we have seen. Now, energy is equal to wavelength is given, so hc by lambda. So first you can find the value of energy. Once you get the value of energy, you can find the number of photons per second emitted from the transmitter. Now part B. The number of photons entering the pupil of our eye per second corresponding to the minimum intensity of white light that we human can perceive is 10 power minus 10 watts per meter square. That's a okay. That is the power per meter. Take the area of the pupil to be about 0.4 centimeter square. You have to convert into meter square, and average frequency of white light to be about 6 into 10 power 14 hertz. Okay. Now So first of all, here you have to see energy E. Then number of electrons. The first part of the question, it is number of photons entering the pupil of our eye per second. That is what we need to calculate. Now, frequency is given. So first we take E is equal to h nu. E is equal to h nu, so that you will get a energy of one photon. You will get now total energy. Okay. Total energy. Total energy in the sense you have to take total energy in this particular 10 power minus 10 watts per meter square is the intensity energy per unit area per second. Okay. Now total energy is equal to number of electrons, number of total energy. It is given total energy per second per unit area is 10 power minus 10. Okay, here the unit is given watts. Watts means joule per second. So energy per second per area is 10 power minus 10, and that will be equal to number of photons per second per unit area into energy of each photon. Energy of each photon is E, or directly we can say h nu, which you can calculate here. Okay, so total energy per unit area per second is equal to number of photons per unit area per second into energy of each photon. So then the total number of photons. So from this equation, you can find the value of n, number of photons per second per unit area can be calculated. Once you get the number of photons per second per unit area, then you can calculate the total number of photons entering the pupil per second. Or can you calculate? You can calculate number of photons per second per unit area into area. So you will get a number of photons per second per unit area into area will give a total number of photons per second. Capital N is the total number of photons entering in the pupil per second. So substitute the value of n and area, you will get the answer. How many photons are entering in the pupil of eye per second? Now, question 26. Ultraviolet light wavelength is given. Okay, 2271 angstrom, and power of mercury source is 100 watt. Then if the stopping potential is minus 1.3 volt, stopping potential, stopping potential is always negative. So no need to take this negative sign. Just you need to take as V naught is equal to the stopping potential. V naught is equal to 1.3 volt. That's all. Okay, retarding potential is always negative. Okay, now then estimate the work function of the metal. The work function you have to calculate. Okay, use Einstein's formula. So work function phi is equal to h nu, but mu is not given, so it's c by lambda. Let's see, by lambda minus e V naught. So you will get the value of phi. Once you get the value of phi, you can use the formula phi is equal to, okay, estimate the work function. So here you will get the value of work function. Phi. Now the second part of the question, how the photocell respond to a high intensity red light of wavelength 6328 angstrom. So here you have the value of phi. Now you have to find out whether you will get photo emission or not. You have different methods are there. Either once you get the value of phi, you can calculate the energy corresponding to this wavelength. How to calculate the energy corresponding to this wavelength? You can use the formula E is equal to hc by lambda. E is equal to hc by lambda. Now, if E greater than phi, then you will get emission. Otherwise, not. Or you can follow another method here. So in this case, you will get emission. You can follow another method. What is that method? Here, you got the value of phi. Once you get the value of phi, again, you can use that value of phi you take. Phi is equal to h mu naught, is equal to hc by lambda naught. Hc by lambda naught. What is lambda naught? Lambda naught is a threshold wavelength. Now using this formula, you find the value of lambda naught. Once you get the value of lambda naught, you compare lambda naught and the given wavelength. What you have studied, frequency should be greater than threshold frequency. If we explain the same in terms of wavelength, then wavelength should be less than threshold wavelength. I repeat, wavelength should be less than threshold wavelength. Then if the given wavelength is less than threshold wavelength, then you will get emission. Otherwise, not. So you have to calculate, find the answer. You can either follow first method or you can follow second method and find the answer. Question 27 again. We have monochromatic radiation wavelength is given. Then stopping potential is there. Electron Planck's constant or and what you have to find out, predict the new stopping voltage. The new stopping voltage you have to find out. So here, what is common you have to see. The emitter is common. Okay. So emitter is common. So in such a situation, what do you have to do? Phi you have to calculate first. Phi is equal to h nu minus e v naught. V naught is given there 0.54 volt. Nu is not there, but nu you can write as c by lambda, substitute and find the value of phi. Once you get the value of phi, then for the second wavelength lambda 2, okay, so you can take as lambda 2, you are asked to calculate what will be the stopping voltage for lambda 2. So how can you calculate? Here again use the same formula. We have EV naught. EV naught is equal to hc by lambda 2 minus phi. Phi will be same because we have same method. Now cross multiply the equation and find value of V naught. V naught is equal to hc divided by lambda 2e minus phi by e. So that you will get the value of V naught. Then question 28. A set of values are given: wavelength and stopping potential. Determine the value of Planck's constant and threshold frequency, then work function, etc. So in simple terms, what can be done here? You can find frequencies nu1, nu2, nu3, etc. Find the frequencies from the wavelength. Then you can draw the graph between stopping potential, and frequency. So here stopping potential we can take, here frequency we can take. Then you have to draw the graph, and the graph is like this, a straight line. Now this way you will get the graph. Once you get the graph, what are the quantities we have to calculate? Planck's constant we have to calculate. Okay, so how to calculate the Planck's constant? H is equal to E into slope of the graph. You will get Planck's constant. Then you have to calculate threshold frequency, mu naught. Threshold frequency is the frequency at which the graph meets this axis, x-axis. So here, this will be the value of mu naught. Then next, work function. Work function here, the y-intercept of the graph you have to take. Or okay, work function phi you can calculate using the formula h mu naught. That is enough. H mu naught you can calculate. Now next, question 29. Work functions of a few metals are given there: sodium, potassium, molybdenum, nickel, etc. Now the radiation of wavelength is given 1 meter away from the photocell. Okay. Which of these metals will not give photoelectric emission? So here again, you can calculate energy corresponding to the wavelength. E is equal to hc by lambda E. So that answer you will get in electron volt. And various energy values are given. Okay, and if the energy given here, these values of energy given here is less than the energy of the radiation, then you will get a photo emission. Okay, so this energy, given energy, is less than the energy of the radiation, then you will get a photo emission. Okay, because always the work function phi is equal to h mu naught, must be less than h nu, that is E. Then only you will get photo emission. But the question, which of these metals will not give photo emission, here you can see when you calculate this value, okay, you will get the value less than 4.17 only. Therefore molybdenum and nickel will not give photo emission. Then the second part of the question, what happens if the laser is brought nearer and placed 50 centimeter away? That means the distance between emitter and the source of light is reduced. Then in such a situation, you can see, okay, molybdenum and nickel are having no change at all. They will not emit any photoelectron, because the minimum condition is a threshold frequency. Okay, the given condition is not satisfied at all. So that wherever be the position of the source of radiation, there is no photo emission in the case of molybdenum and nickel. But sodium and potassium, you will get photo emission. And if you keep the source of light close to the emitter, then intensity of light increases. Repeat, the intensity of light increases. And when the intensity of light increases, what happens? More photoelectrons are emitted. You know, photo current depends on intensity. More electrons are emitted in the case of sodium and potassium. While for molybdenum and nickel, there is no change. Now, next, come to question 30. Intensity of light is given. Then, sodium photocell surface area is given. 5 layers are there. Work function of the metal is around 2 electron volts. Okay. Then estimate the time required for photo emission according to wave picture of radium. The problems of wave picture we have seen already. Anyway, we go for an approximate calculation here. You can see an average atomic area. Atomic area. Usually we take as approximately 10 power minus 20. 10 power minus 20 meter square. It's an average calculation. Okay. Now, number of electrons in 5 layers. Okay. Number of electrons in 5 layers are given. Number of electrons in 5 layers. Already we have given here 5 layers. Then each of them having 2 centimeter square. That means 2 into 10 power minus 4 meter square. And atomic area is around 10 power minus 20 we are seeing. What is the reason we take 10 power minus 20 here? Because you know, when you take sodium, usually we will consider 1 electron. So this is the area associated with 1 atom. Sodium can give 1 electron. So assume that each atom gives 1 electron. So average atomic area means you can almost consider as the area of that particular electron that can be liberated. That's the reason for an average number of electron, we'll take area of each atom. So you will get it. Now next, the power. Okay. So the question, the power per meter square is given. Power per meter square. So total power, almost we can calculate like this. Total power is equal to power per meter square, that is 10 power minus 5 into area is given in the question around 2 centimeter square. So we have 2 into 10 power minus 4. So you will get the answer 2 into 10 power 9 watts is the total power in that area of the photo cell. Okay, while here approximately you will get the answer 10 power 17 electrons. We can almost assume that many electrons are there in these 5 layers. Now, according to wave theory, you know, the energy is gradually absorbed. So this is the total energy per second, and this total energy per second is absorbed by this many number of electrons, 10 power 17 electrons. Okay, so that now you can calculate energy absorbed, okay, energy absorbed per second. per second per electron. Energy absorbed per second per electron is equal to energy absorbed per second per electron. Total energy, it is 2 into 10 power 2 into 10 power minus 9. It is 2 into 10 power minus 9. And we have 10 power 17 electrons are there. So per electron energy will be almost, this will be the answer, around you will get 2 into 10 power minus 26 watts. We take watts because it is energy per second. Okay, now next we have the time required for photo emission. Time we have to calculate. Time is equal to, how can you calculate the time? Time is equal to energy required for one electron. Okay, energy for one electron divided by energy per second. Energy per second. So energy divided by energy per second, then second goes to numerator, energy and energy cancel, you will get the time in second, is equal to, now look at the quantities. Energy for one electron you have calculated already. Okay, energy for one electron, then energy per second, this is energy per second. So that now the question says that work function of the metal is 2 electron volts. So what is the energy to emit one electron? That is 2 electron volt. 2 into 1.6 into 10 power minus 19 is the energy required to emit one electron, divided by energy per second. Energy per second is 2 into 10 power minus 26. 2 into 10 power minus 26, and that is equal to, you will get to 1.6 into 10 power 7 seconds. Okay, so 10 power 7 seconds is a very large number. So accordingly you can see you will get photo emission. You will get photo emission after a long time. Okay, a lot of time will take for photo emission according to the wave theory, but we have seen all these problems. Okay, photo emission is an instantaneous process, it will not take time like this. That is why we say the wave theory fails to explain photoelectric effect. Now come to question 31. Crystal diffraction experiments can be performed using X-rays or electrons isolated through an appropriate voltage. Which probe has greater energy? Which one having greater energy? The wavelength is given. Okay, 1 angstrom, that is 10 power minus 10 meter. Now, first of all, we can take electron. Okay, take electron. When you take electron, we can have a lambda is equal to h divided by under root 2m e, where e is the electron, where e is the energy of electron. So from this you can calculate the value of energy. Energy is equal to h square divided by 2m lambda square. 2m lambda square. Lambda you have to take as 1 angstrom. Substitute the values and find the answer for the case of electron. Next, you have to consider here X-rays. When you use X-ray, okay, energy of X-ray is equal to, which formula we can use, E is equal to Hc by lambda. Again, lambda will be same. Okay, so substitute the values. You can find the energy of X-ray. Okay, then you can compare the values of energy of electron energy and X-ray energy. Come to question 32. Obtain the de Broglie wavelength of neutron having kinetic energy 150 electron volt. De Broglie wavelength, lambda is equal to h by p is equal to h divided by under root 2m e, and energy is given 150 electron volt. So electron volt you have to convert to joule to get the answer in SI unit. So E capital E you have to take as 150 into 1.6 into 10 power minus 19, and you can find the answer. Now see the second part B. Okay, in part A itself there is a second part. Would a neutron beam of the same energy be equally suitable? It's a continuation of question 31. In question 31 we have seen we can use electron beam, X-ray and electron beam are having almost same de Broglie wavelength, so that we can use them to study the crystal structure and all. Now, the same way as you use electron beam instead of using X-ray, is it possible to use a neutron beam to study the crystals? Okay, diffraction experiments and all. That is the second part. Here, the difference is that when you calculate the energy here, okay, so you will get the, sorry, not the energy. When you substitute energy here and calculate the wavelength, when you calculate the wavelength, you will get the wavelength in the order of around 10 power 12 like that, minus 12 like that. Just the order. But we need a wavelength in the order of 10 power minus 10 meter to study the crystal structure. But neutron wavelength, when you calculate, you will get in the order of 10 power minus 12. Okay. Therefore, it is not suitable to study the crystal structure like electron. Then come to part B. Obtain the de Broglie wavelength associated with the thermal neutrons at room temperature, that is 27 degrees Celsius. Hence explain why a fast neutron beam needs to be thermalized with the environment before it can be used neutron diffraction experiments. Okay, again we have to use the same formula for part B also. Lambda is equal to h divided by under root 2m e. But here E, temperature is given. Therefore, for calculating this value, first you have to find energy. Energy is equal to 3 by 2 kT. Energy is equal to 3 by 2 kT. Where when you calculate the value of energy here, ensure that the temperature is taken in Kelvin. Okay. Now, uh, there you can see from the values. Okay. we have to reduce the speed of electron, then only we will get enough interaction time uh, to get, otherwise this wavelength and all, okay, we have to see. So in such a situation we need a suitable energy to fix the interaction time of neutron with the other particles. So otherwise, what will happen? That interaction time will be if the neutron is having very high energy, then interaction time will be very less, so that we will not have enough interaction time to obtain the experiment. Okay, obtain the result of the experiment. Therefore, usually these high energy electrons, I can see thermalized. Thermalized means from very high speed, we have to change it into a medium speed. Okay, for conducting experiments. Then next question 33, an electron microscope. Okay, so electrons are accelerated 50 kilovolt. Now the question, how does the resolving power of an electron microscope compare with that of optical microscope, which uses yellow light? Okay, here also what we have to do, first we can calculate the de Broglie wavelength of electron. In this case, lambda is equal to h divided by root v. Sorry, lambda is equal to this electron source 12.27 divided by root v angstrom. So find the value there for lambda. Okay, you will get the value around in the order of, you have to find the answer, you will get approximately in the order of 10 power minus 12 meter. Now, yellow light you take, yellow light wavelength of yellow light, it is given already there in the order of 10 power minus 7 meter. Okay, now the resolving power is inversely proportional to wavelength. Resolving power is inversely proportional to wavelength, which means the resolving power of electron divided by resolving power of yellow light. When you take this ratio, then the ratio will be lambda y divided by lambda e. Here you will get lambda e. Okay, is equal to, so can see the difference there, around 10 power 5. So what is your conclusion? The resolving power of electron microscope is around 10 power 5 times the resolving power of optical microscope, which uses yellow light. Okay, then question 34. So again, various quantities are there. Now, momentum, you have to find P is equal to h by lambda. P is equal to h by lambda. And here, in this question also, you can see the relativistic mass variation has to be used. Okay, momentum we can directly calculate from there, but for energy calculation you have to use the relativistic energy formula. E is equal to under root p square c square plus m naught square c raised to 4 you have to use, then only you will get energy in such situations. Okay, so you will get a very high value there. You are not studying this formula. Okay, just try to solve this question. That's enough. Okay, so finally you will have a final conclusion that electron will have very high energy in terms of billion electron volts. Okay, energy should be very high in the order of billion electron volts energy. Then next question 35. Find the typical de Broglie wavelength associated with the helium atom. In helium gas at room temperature 27 degree Celsius and 1 atmospheric pressure, and compare it with the mean separation between two atoms under these conditions. So here also you can have the formula lambda is equal to h divided by under root 2m e. Then you can find the value of lambda is given is equal to 3 by 2 kt. Okay, temperature is given, so substitute the value of temperature in terms of in the unit Kelvin, then find the value of lambda. Then question 36, compute the typical de Broglie wavelength of an electron in a metal at 27 degrees Celsius and compare it with the mean separation. Okay, so that also you can just solve using the same formula which we have used in question 35. Find the value of lambda and find the value of E also. Here also temperature is given, so that you can find the same. Now question 37. Answer the following questions. Quarks inside protons and neutrons are thought to carry fractional charges. Why do they not show up in Millikan oil drop experiment? Okay, so you can see quarks are inside the nucleus. As quarks are inside the nucleus, then you can see they are attracted with very strong force. Okay, so in such a situation, as they are attracted with a very strong force, which we call the name nuclear force here. When you conduct the experiment, you cannot consider the quarks as separate particles because they are attracted together. When they are together means, okay, the charge becomes integral values, not the fractional values like this. So that is the reason in Millikan's oil drop experiment, you can see only integral values. Q is equal to NE, integral values for the charge. Because these fractional charges you cannot see. What is the reason? Because quarks are very tightly attracted each other. Once they put together, okay, once they are, we can almost use the term like a combined. When they are combined, then what happens? The effective charge becomes integral charge in terms of 1e, 2e, 3e, like that. Okay, so because of that very strong attractive force, you cannot obtain them separately. That is the reason we cannot see any fractional charge in Millikan oil drop experiment. Then part B. So that's about part A. Part B. What is so special about E by M? Why do we not simply talk E and M separately? So what is the importance of E by M? So there, okay, for a logical explanation, we can take various equations you have studied. You have studied EV is equal to half m v square. kinetic energy formula. Then you have studied F is equal to QE for electron. E we can take is equal to Ma. Then you can have the formula. Okay, yes, in some of the previous problems we have discussed. BV is equal to mv square by r. Magnetic force is equal to centripetal force. Okay, all this we have seen. Now see all these equations, okay, related to elementary atomic or particle concepts. Everywhere you can have E and M. So the behavior of the particle is not only decided by its charge but also its mass. That's the reason, rather than seeing them separately, we will consider them together as a single factor, E by M, the specific charge. Okay, now come to part C. Why should gases be insulated at ordinary pressures and start conducting at very low pressures? Okay, just consider a container. And suppose we have two electrodes here. Now the electric circuit you can complete like this. Then you see that if the pressure is high, then the extent of collision will be very high. So what happens is, suppose a few ions are there in the among the gas molecules, but those ions find much difficulty to travel here because of the frequent collisions. But when the pressure is very low, then the chance of collision inside here will be very less. So there is a possibility an ion present here can reach over the electrode, completing the circuit. But once the pressure is high, the chance is very, very less because of collisions. That's the reason at low pressure there is a possibility for the ions to reach there. That's the reason at low pressure the gas begins to conduct. Then part D, every metal has a definite work function. Why do all photoelectrons not come out with the same energy if incident radiation is not monochromatic? Why is there an energy distribution of photoelectrons? Which means why the photoelectrons are having different energies. That's the question. The question says the incident radiation is not monochromatic, not single wavelength, not single frequency. Okay, so here, oh sorry, why do all photoelectrons not come out with the same energy if the incident radiation is monochromatic? Okay, that means only single frequency. We have E is equal to H. All photons, only these photons are falling there, monochromatic. All of them having same energy. Then what is the reason all the electrons are not coming out with the same energy? We have seen that for a particular metal, work function is constant. And H nu is equal to 5 plus kinetic energy. And for a given metal, phi is a constant. For monochromatic light, H nu is constant. Then what about this kinetic energy? We are observing different values of kinetic energy for different electrons. Why? According to the equation, what we expect all the electrons to have same kinetic energy. Okay, so what's the reason? Let's see. When you take an atom, you can see different energy levels are there. And even that energy levels are not very fine. There is spreading of energy levels like a uncertainty principle and all there. The energy is, we cannot fix the energy. There is a minimum definite spreading of energy level is there. So when a particular radiation or particular energy or frequency is falling in an atom, then you can see it will eject a particular electron. And what is threshold frequency? Threshold frequency is the frequency corresponding to a particular energy that can emit the electron in an atom at the highest energy level. Okay, you need to supply minimum energy to remove an electron in the highest energy level. Okay, Just to think about another electron which is just below that highest energy level, and the radiation is capable of giving the uh, energy which is equal to eject the electron in the highest energy level, also the electron in a level which is just lower to the highest one. So both these electrons are ejected. So in such a situation, the electron in the highest energy level will have maximum kinetic energy. The electron which is also ejected and just below the highest energy level is having less kinetic energy. So in simple terms, we can say during this photo emission, electrons from different levels may be emitted. According to the level, you can see their kinetic energy will be different, and this is actually we can explain due to the small extension or spreading of the energy band in the atom. The energy, it is not precise energy, very small spreading, maybe 1.1, 1.05, 1.04, like that. Small spreading of energy level will be there, which we call the name energy band. Because of that, slightly different energy levels only, electrons are having different kinetic energies during photo emission. Now, part E, the energy and momentum of an electron are related to the frequency. Okay, equations are given. Now, while the value of lambda is significant, but here the nu is not significant. So what's the reason? So in the case of the matter wave that you have to see there, matter wave. Okay, lambda is important because lambda is the wavelength of what is that? Lambda is a central wavelength of the wave packet. That way we can take. So it is important. And lambda will give the feature of a wave packet. Now come to frequency. We have the formula V is equal to mu lambda. And what is this speed? This speed is actually the speed of individual wave in the wave packet. So we have the wave packet like this. Okay. Now this V is the speed of individual waves. While this wave packet, the way this wave packet is associated with the particle, the total wave packet has a velocity which we call the name group speed. Group speed I will write as Pg is equal to P by M, because de Broglie wave, matter wave is associated with a particle having mass. So its velocity of the entire particle, Vg, which we call the name group velocity, is equal to P by M. It is significant. But what do you get from the formula V is equal to mu lambda? This wave velocity of the wave within this package. When this particle is in motion, particle velocity is important. But what about the velocity of the waves within the package? It's not significant. As it is not significant, this mu has also no significance. So what is significant? The group velocity is significant. This velocity we call the name phase speed. Phase speed. Phase speed is not significant, so frequency is not significant. Okay, because that happens only within the package, within the wave package. Okay, therefore we can say lambda is significant, but mu is not significant.